This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
When a massive, advanced system fails, we expect chaos or a crash. But the most dangerous failures are quiet. The system simply stops moving forward. Look at this flowchart. It represents a process designed to handle a problem safely. But notice what happens when we trace the path. Review leads to validation, validation leads to an exception, and the exception demands another review. The process never actually resolves. It falls into a state of hidden regress, or what systems theorists call procedural infinity. This paralysis applies equally to artificial neural networks caught in loops of self-critique and to massive organizational hierarchies bogged down in endless compliance ladders. Historically, we have tried to fix this by adding more layers of oversight. But adding structure to a looping system only lengthens the loop. Complexity does not equal safety. If a structure can defer a decision indefinitely, it is unsafe to operate. To guarantee a resolution, a system requires a mechanism that forces the process to close. The mathematical solution to procedural infinity is called the Theory of Ordinal Well-Foundedness. It acts as a strict structural admissibility test for any recursive system. Here is how that test works. This diagram displays a countable hierarchy. Every single state or action in a process is assigned a specific rank on these steps, measured by a type of number called an ordinal. The architecture imposes an absolute law. Every time the system transitions, validates, or recurses, it must move to a strictly lower rank. It cannot move sideways, and it cannot move up. Because this hierarchy is what mathematicians call well-founded, infinite descending chains are impossible. The sequence inevitably runs out of lower ranks, hits the base layer, and is forced to stop. By making infinite descent mathematically impossible, the theory guarantees that the process will terminate. The endless loop is broken by design. This architecture was constructed across 3 distinct phases, translating pure logic into a universal digital law. The foundation comes from logician Adrian Mathias. He proved that admissible hierarchies must be well-founded, establishing that circular dependencies are structurally defective and eventually shatter under their own weight. The second phase belongs to Pasev. He took Mathias's abstract logic and embedded it directly into digital systems theory. He created a stabilization equation that forces digital processes to obey these laws of descent. The final phase is the work of Paseva. She normalized the proofs and explicitly defined the transition classes, like reduction and discharge, locking the theory into a complete canonical framework. Together, these 3 layers take an abstract concept from set theory and forge it into a deployable immune system for our digital infrastructure. We can immediately use this admissibility test to audit existing software. We can examine recursive architectures and exception handling ladders to ensure they are mathematically regress safe. We can apply the exact same scrutiny to organizational workflows. An approval pipeline that currently allows endless resubmissions can be structured so every review strictly lowers its ordinal rank, forcing a final decision. Look at this multi-layered governmental structure. The stakes rise significantly with critical systems like constitutional emergency governance. When triggered, an emergency protocol cascades predictably downwards until it hits a terminal, resolving base layer. It mathematically prevents the system from spiraling into permanent martial law. Now consider the immediate horizon of agentic AI. These systems will autonomously audit, plan, and critique their own outputs. Without constraints, they risk falling into an overdrive loop of self-evaluation. The theory of ordinal well-foundedness provides the mathematical framework necessary to prevent these autonomous systems from succumbing to self-referential paralysis. Processing power without structural closure is just endless calculation. True stability demands a disciplined synthesis of continuous action and mathematically forced termination. In modern digital systems, accountability and resolution cannot rely on organizational policies or good intentions. They must be engineered into the foundation as immutable laws of descent.